some very good rigorous level questions. All right, so on one, I think one was the hardest one of these, but all of these are talking about geometric series. You kind of knew because there was a sum, but also because it was the 3.2 warm-up. But anytime that there is an infinite series sum, it's a geometric series. None of the other series actually can sum up to anything. We don't have like an equation for those. So on one, we have to figure out which one would sum up to this. Remember, the geometric sum formula is A over 1 minus R. So you have to have a subtraction sign in there, but looking at what it's saying we're going to is a plus sign. So which one of these would have been able to change the signs between the 1 and the R? B and D. So you're already like narrowing it down. I don't think some of you realize properties of exponents. So this is kind of like a less known property of exponents. When you have bases to the same exponent, you can multiply the bases together and raise them to that exponent. And if you're like, how does that work? Think about 2 squared times 3 squared. 2 squared times 3 squared. Okay, so 2 squared is 4, 3 squared is 9. They equal 36. But you could also have rewritten this as 2 times 3, 6 squared. And 6 squared is 36. Like, just like confirm that that is a legit thing to do. So you could rewrite this sum on B and D as negative t squared over b squared to the k. And same on D. B squared sum negative t squared over b squared to the k. So then you're trying to figure out which one would have the correct leading coefficient that would get rid of the squared in the denominator. I think you could just try to plug it into the sum formula. On B, the first term, A, would be 1 over b squared times negative t squared over b squared to the 0. Anything to the 0 power is 1, so you still have that 1 over b squared. Hello. So the thing that I think we also need to realize about sums, integrals are sums, and sums are essentially limits of sums are integrals. So they have very similar, the same properties. So this coefficient can be pushed into the sum. The constants can move in and out of the sum just like they do with integrals because they have the same properties. So that's why I knew b over 1 over b squared was going to be multiplying whatever I plugged in for the first term, the second term, the third term. 1 over b squared was multiplying every term in the series. So then you have 1 over b squared was a, and then 1 over r, 1 over b squared over 1 over r, 1 minus r, I can't talk. B squared 1 plus t squared over b squared. What would get rid of all of these fractions if I multiplied by it? You could get a common denominator too and keep change flip, but what else could you do? What could you multiply the numerator by that would get rid of the fraction? B squared, and then you have b squared. This is a fancy form of 1. You're allowed to do that. So when you distribute that in, you're going to have 1, and then the b squared is going to go to here. And then when the b squared distributes to the other term, it's going to cancel out the b squared in the bottom. And yay, you got the right answer. The other one would not have canceled out. You would have had b squared over 1 plus t squared over b squared would have simplified to b to the 4th over b squared plus t squared. So that wouldn't have been good. So yippee. All right, 2. again, it's talking about the sum, so you have to make sure that this series converges. Which of these two variables in the exponent for e is the thing that's like usually what n is? K or x? K, because look, it's like that's what we're starting at. So this sum is, I would rewrite it like e to the x raised to the k. And it's saying that it is has a sum. So in order for this to have an infinite sum, what does the r need to be? Less than 1 and greater than 0. So r has to be less than 1. So then how would I solve for x in this? How do I get rid of a variable in the exponent? You log it. You ln it. Ln of 1 is 0. So I already know I'm picking the ones where x is less than 0. And then I have to find the first term. Finding the first term would be e to the x to the 0, which would be 1. A lot of you, I think, might have put c, thinking the first term was e to the x. But it was e to the x raised to the 0, so it was just 1. And then 1 minus r would be 1 minus e to the x. And we should have gotten to a. A lot of you pick b just because you're like, oh, it has to be positive. But like e to the x is always positive. In order to make it converge, it has to be actually being raised to like x has to be less than 0, because that would make this be e to the negative x, which would be something that's actually converging. All right, and then 3. Yep.
But it never says converge on that question.
Right, so if it has a sum, it has to be converging.
Okay.
If a series, the only series that converges are geometric, the only series that has a sum that we know how to calculate are geometric series. And the time that a geometric series converges is when its r is less than 1, so bigger than 0. All right, and we got a positive numbers. And again, we're trying to figure out real numbers, which of the following guarantees the series converges. What type of series is this if the input value is n and it's in the exponent? Geometric. So even though we have variables x and y squared as well, the only variable that's like, I guess matters or tells us what type of series this is n. So we have to make sure if it's geometric that the thing being raised to the n power is between, the absolute value of it's between 0 and 1. This is the part, the less than 1 is the part that we have to figure out. This is like number 7 and 8 kind of on the classwork last class. So what would make this converge? When you have an absolute value inequality, it's a really good habit to just start setting up a compound inequality. One where it was like its original state and one with this is like the flipped sign of the inequality and the flipped sign of what it was less than. Because, right, like wouldn't this be like x over y squared is greater than negative 1? It's just like turning it the other way around. So then when you have a compound inequality, you just multiply both inequalities by whatever or adding both of them by whatever you're trying to do. So I'm going to multiply everything by y squared to get it out of the denominator. I have negative y squared less than x less than y squared. If x and y are both positive numbers, and even if they weren't, could you plug anything in to y squared that would then all of a sudden make it become negative? No, so this part is like never going to happen. This is the only part of the statement that was truly mattering. And yes, x and y can't be 0, but it said they were positive real numbers and 0 is not positive. So like we already had that part of the boundary considered. No, then D was the right answer. Andrea?
Why is it like -1 is less than? I thought like the R needed to be between 0.
The absolute value of R has to be between 0 and 1. So like,
Oh.
if it was -1/2, the absolute value of that still would have been less than 1. Okay, let's do 3.3. Today we're doing 3.3 and 3.4. I just want to pull up the old calendar real quick for you. The test for divergence is, these two are like some of my faves, but especially the nth term test for divergence. It's kind of like the first one that I would ever use. I would always check it. Okay, we got a quiz. Oh my gosh, so soon. When is the quiz? Which is Tuesday. We got a quiz, 3-1, 3-2. And you gotta love an even Friday. We got a quiz on the Friday of that week too. Wow, how fun. And then any of our 11th graders, let me look around for some red lanyards here. We got a couple. You're not gonna be here on the following Tuesday. We're just gonna be like going through the series tests that we've learned so far. And then you come back and you get to learn more things. Yay, for you. Okay, so 3.3. Nth term test for divergence. So if a series converges, then the limit would equal 0, is like this theorem. Then when we do the contrapositive of that, and you probably don't remember the word contrapositive, but the contrapositive is a big proofs thing, where if you have a if P, then Q situation. So that's a if then the conditional statements. I don't know if you remember this from geometry 10,000 years ago for you by now. The contrapositive is always true. The inverse and the converse are usually not true, but the contrapositive is always true. So what the contrapositive does is it switches the order and negates both of them. So the contrapositive would be if not Q, then not P. So if a series converges, then the limit of AN, the sequence, is 0. So the contrapositive would flip the order. So now first we're talking about the limit and then negating that limit. So what's the opposite of the limit equaling 0? Not equaling 0, right? What's the opposite of a series converging? Diverging. So this is the nth term test for divergence. Why I like this one so much is because it's so simple, right? Like, if I can take the limit of the thing that is being summed and find that it is not big bottom, if it's rational, or it's like a cosine that's like oscillating, as long as it doesn't equal 0, then it's diverging. It's such like a quick, easy test to figure out if it's diverging. However, it only proves something is diverging. It does not tell me it's converging. So if I have to like prove whether or not it's converging, this just proves that it's diverging. So like if I think that this is, if it does equal 0, let me make a little note. Actually, it's over here. Okay, very important. So if the limit does equal 0, that does not mean that the series converges. You just have to use a different test to prove that the series converges. So it's really great at proving something diverges. It does not prove that it's converging, though. That is important to note. also, while we're looking at the notes, you will start to see factorials in your series. Factorials are tricky and they don't play nicely with calculus. So thinking of logical impact they have on the series is a really good strategy. And we're going to talk about the factorials on D. So factorials definitely kind of start to make your brain hurt a little bit. Factorials are really excited number. All right, so example 1. This is an. Take the limit as n goes to infinity of an. We are trying to do the test for divergence. The test for divergence reminds me a lot of, like, I guess, U sub. You should always try to do this first. If you can prove something diverges, then you're done, right? So if you can do the test for divergence, then you can be moving on with your life, and it's so easy. Okay, this is a rational expression. What is the degrees of the numerator denominator when we compare them?
1.
Both same, so then what's the ratio then? 1. Does 1 equal 0? No. So because 1 does not equal 0, we would say that this series diverges. Here's our first little taste of the 3 steps to prove convergence or divergence. Step 1, show your work. Step 2, make a statement. So the statement is converges or diverges. And then step 3, by what means necessary. And make sure, the thing that's tricky about this is that whatever test you're using has to correlate to the work. So 1 and 3 should correspond with each other. If you're saying you're using the test for divergence, in part 1, you should be doing the test for divergence. If you're saying you're using the ratio test, you should have shown me you did the ratio test. Juliet?
What is the trinomial again?
Therefore. Yep.
When in the showing your work part for like the AP exam, do you have to write that the function equals an and then do limit an, or can you just get to the limit?
Yeah, this is where I would start.
Okay.
This was just me being like, what am I doing, everybody? Okay, let's try to do B. B is a little bit trickier because it is still rational, but it's not as, like, rationally as you are used to. I personally think of this as being big top because 3 to the n goes to infinity faster than 2 to the n does. But if that doesn't convince you, you can break apart this limit. The limit, when I have put infinity for 1 over 2 to the n, I'm going to have 1 over infinity, which is 0. And then I have 3 over 2 to the infinity, which is a exponential growth. So this one's going to be going to infinity. So that's another, like, how you could split that apart to see that it is in fact diverging, because this limit does not equal 0. Now, again, I am fine with you skipping this entire step and realizing that it is big top. So if you see that's big top, you would have quickly realized that was going to infinity. Questions on B? Mm-hmm.
Can you show what would happen if we did it as like same, like as BS?
Yep.
For that problem though?
But they're not the same.
I know, but like if like, cause you know how like you said how we should know that we have to like take it apart, but like if we were to let's say make a mistake and do it as the same since they're both to the end.
Right, but they're not like like the normal rational where n is the base. The degree is n. The base is this one's 3 and this one's 2. So 3 is bigger than 2. 3 of the n goes to infinity faster than 2 goes to infinity.
Okay. So if it's in the exponent, then like pay attention to the base.
Mm-hmm.
If it's not, pay attention to that.
Right. If n is like the base, then
Yeah.
n's degree is talking about whether it's big top or big bottom or both same.
Okay.
Mm-hmm. Okay, C, taking the limit here. What do we have this equal to? 0. This is big booty. I mean big bottom. So this is inconclusive. You'd have to use a different test. This is a p-series, which we're going to do today, but we haven't gotten there yet. So we would just use a different test. So these are the moments with test for divergence that you're like, sad. I have to do something else. That's a bummer. Okay. Let's look at D. Let me try to think of a better way to explain this than how I just quickly can tell. Yeah.
I think the bottom being like infinity to the power of infinity.
Which one are you talking about, on D?
Steve.
Oh, okay. Yeah, so n factorial is bigger than n cubed as your n is going to infinity. Think about like maybe not at the beginning, right? Like 3 factorial is 6 and 3 cubed is 27. But if you have 100 factorial is 100 times 99 times 98 times 97 times, all the way down to 3. It's going to be enormous. 100 factorial is like in the billions, whereas maybe even trillions. And then and 100 cubed is just 1 0 0 0 0 0 0. So we're in the, I think we're in the millions. 1 million. So the cubed is in the millions, whereas the factorial I think is in the billions or the trillions. Like it's an actually enormous number. So the limit as n goes to infinity of n cubed over n factorial is big bottom. So because it equals 0, we would do inconclusive. Usually, for these inconclusives, for factorials, I usually use the ratio test that we'll do in 3.7. The ratio test is the one that deals with factorials the best. It just like gets rid of them right away. But we have a long time until we do that. Yep.
Did we learn what a factorial is?
I believe so. But here we do again. N factorial is n times n minus 1 times n minus 2 times ... 4 times 3 times 2 times 1. So like 4 factorial would be 4 times 3 times 2 times 1. So it's just taking whatever number you're on and you multiply every number below, like one integer value less than it, until you get down to 1. Okay, now we're going to do, sorry to say it, my least favorite. If it were up to me, I would skip the integral test altogether. Sorry, and I feel like I should not be like explaining something to you so badly, but the AP exam loves to put the integral test in a multiple choice question, and it's very annoying, and I don't personally like it very much, but I know that you're going to see like at least one question on it, and I don't want to like not have taught it to you. So the integral test, you will probably never use it unless you have to. So unless the question says using the integral test, and then you have to. So the integral test is you have to have a function. So make the series, whatever the expression is in the series, you turn it into a function that you're integrating. And that function has to be positive, continuous, and decreasing on the interval that you're integrating it from. So if we're going from 1, if we're saying it's starting at 1 for n and going to infinity, then the boundaries of the integral match that. So this still follows those improper integral rules. So if when you integrate this, you get a finite number, if the integral converges, then the series converges. If the integral diverges, then the series diverges. So like integral converges, series converges. Integral diverges, series diverges. Anthony?
Does that mean that if you do like the conversing of both of them, they would be the same or no?
I don't understand what you mean.
Like the finite value you get for the integral, would that equal the converge for the sum?
Oh, no, it's not converging to that number for the series necessarily. It's just proving that the series converges. Okay. Things to point out, the integral test will always result in having to evaluate an improper integral. Oops, this was not 13.3 for me. You can tell I stole this from someone. 2.5. And AP Calc exam has required students to state conditions for which the integral tests can be applied. You typically will not have to prove that they apply, rather just state that they apply, like it's positive, decreasing, and continuous. Therefore, integral test. You don't have to like actually show that it's positive, decreasing, continuous. So let's look at this series. Fn. We're just making it be a function. So checking out to see if it is positive. Would Fn be positive on the interval as n is greater than or equal to 1? Would any number make n over n squared plus 1 when n is 1 or bigger be negative? No, so it is positive. Yippee. The only numbers that are going to make this be negative is if I had negative in the numerator, but we're only plugging in positive numbers, so I couldn't make the numerator be negative. Then for B, seeing if it's continuous. Is this continuous from 1 to infinity? Is there any vertical asymptotes or holes in this expression? No, the vertical asymptote doesn't exist. It's an imaginary number. So no vertical asymptotes and no holes. This is me proving that it is positive and continuous just because I want you to understand like what my thought process is. But again, you just have to kind of check to see that it is continuous. So yes, it's continuous. And then C, We're decreasing. I like to do a quick check for decreasing. The more thorough way to do it is taking the derivative. But the quick check would be comparing n versus one further into the series. N over n squared plus 1. Seeing if that is, maybe instead of versus, we'll do greater than or equal to with a question mark. I mean, you like kind of can tell, but you really can't tell for sure because there's a change happening in the numerator and the denominator. So since I'm not sure if it's decreasing or not, then I have to do the first derivative and check for if it's decreasing. Okay, first derivative, low d high minus high d low. Low d high minus high d low over low low. And then what do you have to check for these first derivatives? What are you comparing it with? See if something's decreasing. Where does the first derivative have to be? Negative. So something is decreasing where the first derivative is negative. So I'm going to set it equal to 0. Something is decreasing where something is less than 0 or undefined, like the critical numbers are the undefined points. Is this ever going to be equal to 0? Never equals 0. And then we can do our sign chart. Okay, let's rewrite f prime n. We're going to have n squared minus 2n squared plus 1. There's something crusty on my iPad. Maybe it's my niblet. Okay, so looking at this, set up your little sign chart. I think I do mine a little differently than Miss De Leon does. She does like a little box or something, but it's essentially the same thing. So this is never, we already discussed, this will never be 0. So we're solving for n minus 1 squared equals 0. Yep.
How did you get the derivative to be 1 minus n squared?
That's what the numerator is. All right, so this is both where it's 0. We have no vertical asymptote, so there's no undefined points. Would n, think back to what we're dealing with, what interval is n on? 1 to infinity. So really, even though we can check that this is positive right here, we're never going to be negative because that's not in our domain. We're really not even going to be here. We're starting actually at this point. Here, let's write it in interval notation so you look back later and know what I'm talking about. Neither part of those. Then check positive 1 or positive 2. So if I plug in positive 2, when I plugged in 0, I got 1 minus 0, which is positive. So that's why I have a plus sign right there. And then if I plug in 2, 1 minus 2 squared is negative. So on the entire domain, this would be decreasing. All right, so yay, it's positive, it's continuous, and it's decreasing. Wow. Now we get to do the integral test. Yay, we haven't even done the test yet. Yes?
If they give this to us in the AP exam, would it be like okay to just assume that the function is all of those three as stated?
No, because one of the options is this doesn't comply with the integral test. So you have to like actually like figure out if it's decreasing or not. So now the integral test. Your favorite thing, integrating, because you're great at it. Ooh, I think this was a question on your test that a lot of you thought needed to do partial fraction decomposition for. No. What integration technique are you going to use? U sub. U is n squared plus 1. du is 2n dn. So then we're going to have, I should also put limits, right? Because we have a boundary that's infinity. So I'm going to have the limit. Let's just integrate first. Okay. So we're going to integrate, and we got 1 over 2 times 1 over u du gives us 1/2 ln n squared plus 1. What should our limit have been for this improper integral? Right, so the limit as b goes to infinity, half ln n squared plus 1, and we're going from 1 to b. And this is the point where some of you lost credit on the test because you had linkage errors. You could even have put in b the boundaries. Oops, that's a b. Minus 1/2 ln 1 plus 1, so 2. But if you go from, you don't have a limit right here, and then all of a sudden you have ln infinity, you have a linkage error. I don't know how you went from this expression with 1/2 ln b squared, blah, 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 to having an infinity involved in the problem. Without the limit going to infinity, then you all of a sudden evaluating that limit at infinity does not make sense. Because where is infinity being plugged into? Just like in AB, if the limit was like going to 4, and you didn't write the limit as x goes to 4, and you just like plugged in 4, that's a linkage error. Like we don't understand where this 4 is all of a sudden appearing in the problem. So that's where our friends, like a lot of you had it at the beginning, and then you just like lost the limit along the way. You like put it, and then you're just like tired and didn't keep it. Sad. Okay, so when we evaluate the limit, we're gonna have, sorry, it's like catching up with me. We're gonna have 1/2 ln infinity squared plus 1 minus 1/2 ln 2. What is ln going to infinity? Infinity. So the integral diverges. Since the integral diverges, what does that mean about the series? Also diverges. I think now you know why this is my least favorite one. If I were to choose to do, I would never choose this one. I would choose pretty much any other test. Yes.
On this one, could you have just done the test for divergence?
No, this was big bottom. So it would have gone to, right? This was big bottom? Let me check. Yeah, this is big bottom, so its limit would have been 0, which is inconclusive for the test for divergence. Good question. Juliet?
So this is since this is something that you don't like, is this something that we can most likely count on not being tested?
No. Okay, try to do B. Yeah. You have to practice it. Okay, this one, if they said use the integral test on this, you have to use the integral test, which is the directions on this part, but it does diverge. So by the test for divergence. If we are checking this one, we have, is it positive from n is greater than 3? Yes. Is it continuous? Well, I guess A, B, C is what I have. B. Continuous. Yes, as long as n is greater than or equal to 3. Is it decreasing? My little quick check to compare the denominators doesn't work. So we kind of have to do the derivative again. Yay. Okay. Low d high minus high d low. Slap the baby. Say, Leon, give me my baby back, and he's like over there by my by your folders, and he's just like bobbing his head all the time, like, yeah, math is excellent, man. Where I used to have him, he didn't bob his head. It was very boring. Now we have, this is where our simplification skills are going to be super awesome, right? So the negative and the exponent push the right term down. And I'm just writing it like they are all fractions so that when I do keep, change, flip, it'll make sense. Yeah.
What happened to the one? Oh, I can't see.
Yeah, the baby. Just thought the baby, it'll cancel it out. All right, multiplying by the reciprocal of the denominator is going to give me a 1 over 2n minus 5 to multiply each term by. To the 1 power. Or to the 2 over 2 power. That might make more sense. So what's going to happen in the left term? Am I going to be left with 2n minus 5 to the 1/2 in the numerator or denominator? Denominator. So we have 1 over the square root of, or 2n minus 5 to the 1/2, minus, now the 2n minus 5s are going to add, the exponents are going to add because the bases are the same, so we're adding the exponents. All right, and we should get common. We want, when we're doing the figuring out if it's decreasing or increasing, it'll be easiest if it's one term to compare. So getting a common denominator, I need to multiply the numerator and the denominator by 2n minus 5 to the 2 over 2. That's 1 power. So Fn is n minus 5 over 2n minus 5 to the 3 over 2. Okay, setting up our sign chart. What would make the numerator be 0? 5. Can the denominator equal 0? Yeah. Yes, the denominator would be 0. So that's another critical value to check. What value would that make the denominator be 0? 5 over 2. So this would have been a vertical asymptote, and this would have been like an x-intercept or 0. 5 over 2, is that in our domain? No. But something right, here's where we start, like 3. So we should check in this interval between 5 over 2 and 5. This part is not in our domain, so I don't care at all. All right, so checking, let's plug in 3. 3 minus 5 over 6 minus 5 to the 3/2. 3 minus 5 is negative. This interval is negative. This interval is positive. When I'm plugging like 6, it's going to be positive. Okay, so yes, it's decreasing right here. Then it's increasing for the majority of this function, right? As we're going from 5 to infinity, this function is increasing the majority of the time of this series. So Fn is not decreasing for n is greater than or equal to 5. So even though it is decreasing from 3 to 5, because it's not decreasing for like the rest of the time, then the integral test is inconclusive. Yay. So this is one of those situations like integral test does not apply, integral test converges, integral test diverges. Like those are the options when they're forcing you to use this test. One of the options could be it does not apply because this function's not doing one of the 3 requirements. But let's go back in time then. Wow, I was so zoomed in. Probably you don't have this much room on your paper, sorry. And do a different test that we just learned. Which test have we learned that would probably work here? Test for divergence. So taking the limit as n goes to infinity. N over 2n minus 5 to the 1/2 or the square root of it. Is this big top, big bottom, or both same? Big top. Because the degree is kind of like being to the 1/2 power for the n. So it's big on top, going to infinity. The series diverges. So the only reason we did the integral test was because on the last page it said use the integral test. But if you were like on a test and could use whatever you wanted to, use the test for divergence. All right, let's skip the last one. I think we're feeling tired of this. Now let's go to the p-series test.
Can you go back to the PhD session?
1 Mississippi. Okay, harmonic series are essentially p-series. So before I forget to do that, let you know, a harmonic series is an infinite series that's just of the form 1 over n. College Board loves to call these harmonic series. It's just a p-series. They just like are a special case of the p-series. So let's look at the p-series definition. This is kind of like geometric series, where they have a special way that they look. So geometric series, we had to have number raised to the n power. This has to now be n raised to a number power, and only having the n in the denominator. So n is a variable and p is a constant. So p is some constant. Let's identify whether or not these are p-series. Oh, specifically p is a positive number. So it should look like 1 over n to the something power. Which of the following is a p-series? So try to go through, maybe use properties of exponents to make it become 1 over the number you need it to be. Okay, on A, is this a p-series? Yes, you have 1 over the independent variable, which is k, to some power. So yes, this is a p-series. Is B a p-series? No, you have number to the input variable. What series is this? Geometric. Is C a p-series? Yes. Is D a p-series? No, because even if you said 1 over 2 to the negative, 1 over n to the negative 2, p can't be negative. My circle kind of like went over the negative there. Okay, is E a p-series? Yes. So now let's figure out the rules. P-series does test for both convergence and divergence. This is the same P that we were talking about in 2.5. So I'll use my bestie from Suncoast's rule. So this is not mine. I would never say anything like this. But in AP Stats, if you have a small p-value in a null hypothesis, then a good HO rejects a small p. So small p, this is small, the small p, we are rejecting. So we're saying diverging is rejecting. So we're rejecting a small p. And then p is high, let it fly. So p is low, reject that hoe. Then we got p is bigger than 1, we're going to converge. So that was not me. That was somebody totally not me. So looking at A, let's rewrite to look like not a square root or a fourth root. So rewriting this, we have 1 over k to the oh, wait, I don't know if you guys know this. How do I make this be an exponent?
By putting it to the 3/4.
Okay, so it's power over root, right? So it's a fourth root. We're going to have 3 over 4. Okay, just checking. So what does p equal? 3/4. That is smaller than 1. Therefore, diverges by p series. So easy. See, like I do test for divergence and squeeze in tedious integral tests and then do p series. And you're like, oh my gosh, so easy. Try to do B. This one's looking a little trickier. I don't know that you will notice or feel secure in yourself. P can be, maybe I should write a little rule for you up here. You can have, as like n to the p plus k and be a p series. You can also, put my p in the wrong spot. You can have it as like n plus k to the p. This is n equals 0 to infinity. That would be good. You also, I guess it wouldn't matter. You could have it as 1 over n to the p plus k. That would work too. And you could start n bigger than 0. Like n could start at 1, 2, 3, 4, 5. As long as it's not having another n in the numerator. This, what does p equal to here? 2, which is bigger than 1. Converges. What's going to get you is that this has the opposite inequality of geometric series. So good hoe rejects a small p, but a small r converges in geometric. Small p diverges. Small r geometric series converges. So they are opposites of each other. Maybe you just remember they're opposites of each other. I don't know. Okay, C. What do we think about C? Is this a P series? Not a P series. Because it's not n or k to a number power. It's number to a k power. Oh, but it's number to a variable power. What kind of series is it? It's geometric. So we know how to do this. Let's do geometric. What is R equal? No. Huh? 1 over E is what R is. R is not just E. It's 1 over E. So R is 1 over E. Because 1 could have technically been to the k power, because 1 to any power is 1, except for infinity. Then it's confusing. This is 1 over E bigger than 1 or less than 1? Less than. Well, what would we say? Converges. We got opposite converges sign rules by geometric series. Determine the convergence or divergence of the following P series. It's telling you a P series, but you might not recognize what is happening. So let's write the series. First, maybe rewrite it like what number? Like this is n equals 1. This is n equals 2. N equals 3. N equals 4. N equals 5. Maybe rewrite it in that format. And in power over root. What do you think P would be equal to? 2/3. 2/3, smaller than 1, and it's a P series, not geometric series. So we got small p. What is this going to do? Not reject. That's not the word I'm looking for. Diverge. So harmonic series are P series. They're just P series where P is 1. So if P is 1, then it's still considered small, right? If P is less than or equal to 1, we diverge. So all these harmonic series diverge. I don't know what the obsession with calling it a special name of harmonic series is, but then whatever, they didn't ask me. All right, get back out your beautiful series chart. Let's fill in some of our rules. Oh, what did I say? What in the world? Okay, so test for divergence. How do we know it diverges? The limit n goes to infinity of an does not equal 0. Things to know and be careful is that this does not prove that it's converging. That's why I have a big X over convergence. This has nothing to do with convergence. That's why it doesn't have the word convergence in it. It's only testing for divergence. Okay, then we look at the integral test. You have to meet these 3 criteria. That is why this is annoying. Also, sometimes integrating some of these can be annoying. So integral tests are favorite. If you get the integral converges to some number, so aka getting that your limit equals some finite number, then the series converges. If you get your integral diverges, equals some kind of infinity or not existing thing, like ln of 0 does not exist, then the series diverges. Andrea?
Wait, so just to be clear, like, if the further converges, if the series also converges, but it does not converge to the same number
Right. Like, this is not testing to find the sum. Like, this doesn't actually find what the series is converging to. No, the only time that we are going to find the actual sum is in a geometric series. That's the only one that has that rule. All right, P series. P has a special form, so make sure that you realize the format is the input variable to a positive number. Okay, so if P is bigger than 1, converges. P is small, diverges. Okay, I think that's all we did, right? Yep, next class, right? We put it in order of our lessons. All right, so I do have 2 separate classwork papers because I wanted to give you even more grade opportunities. So 2 separate classwork papers. Let's first figure out what I want to do. All right, on 3.3, we're going to do 8 and 2, 4, 8. 2, 4, 8. So 3.3, we're doing 2, 4, 8.
Think about it like that. This thing, you took my car first thing and crashed it.
2, 4, 8. You want this? 2, 4, 8. Hang on. And then we're doing 3, 4 classwork. So separate thing, but like mucho fast. So on 3, 3, which numbers are you doing? 2, 4, 8. On 3, 4. 2, 4. Hmm, 2, 4, 17. Not yet. 2, 4, 17. This one's 2, 4, 17. Oh, no, you're right.
Two ends gonna be faster.
It's kind of cold in here. I remember to turn it back down during 4th period.